Hi guys, welcome back to another video. You guys really seem to like when I took you along for the journey of Flappy Bird, so let's do it again. This time I'm going to make a game called 2048 with just Redstone. 2048 is a desktop and mobile game released in 2014. You have a 4x4 grid of squares which can hold tiles. The goal of the game is to create a 2048 tile by merging other smaller tiles together. The controls are up, down, left, or right, and when you do any of those, the tiles will be shifted in that direction. If any tiles hit each other that are the same while they're shifting, they merge into a tile that's twice as big. So naturally, all of your tiles will end up being some number 2 to the power of x because they keep doubling every time. After every move, a new tile spawns in a random spot, and that tile is usually a 2, but it also has a 10% chance of being a 4. You can also just keep merging after 2048 if you want to. It's an arbitrary decision to stop there. My personal best is the 8192 tile, and it was on a school computer. Oh, I'm probably not supposed to say that. Let's start with the easiest part, the display. I'm going to do a lamp display again. This seems like a decent size for a tile. Since we only have to show numbers, the type of display that comes to my mind is a 7-segment display, which uses 7 segments to display any number. You've probably seen these before on digital clocks. The smallest possible 7-segment display looks like this, only taking up a 3x5 area. If we use 4 of them behind a tile, this is how it's going to look, and honestly, I think it looks pretty good. Actually, I just realized a problem with this display. I can't put every number in the middle, right? I can put 16 in the middle, and I can put 2048 in the middle, but 128, I have to either put it on these 3 digits or on these 3 digits. Yeah, I think we're gonna have to go with a completely customizable display instead, because that way we can put every number in the middle. Plus, I already know I'd get so many comments about it not being centered if it's not centered. Okay, here's my first idea for a programmable display. You just have 5 pistons, and each one starts an observer clock, which will only follow a specific chain and only light up 1 lamp at a time. Let's put this on the display. Okay, I put it on the display, and now we can write any number we want, and more importantly, we can put them all in the middle. But we need to be able to display lots of different numbers, not just 2048, so let's make a bunch of ROM lines that will store the numbers for us, and then we can switch to any number we want. Okay, I made a bunch of ROM lines, and now we can display any character we want, all the way from 2, 4, 8, all the way to 8192, because why not? So when we turn on 32, for example, this entire line gets depowered, and all the torches attached to it get powered. These torches are coded for the actual pixels of 32, and so when we look at the screen, it shows 32. Or for example, I can turn on 512 and we get 512. All right, awesome. We already have a tile that can display every number we need. Now it's time to start thinking about representation. We're going to be doing logic with these tiles. We're going to be moving them around, merging them. So how do we want to represent them in the hardware when we go to do that? Well, we only have 13 different numbers that we can display, and 13 is less than 15, so why not signal strength? We can just represent every tile on the board with 1 signal strength value. I mean, they might be a little bit harder to move around than binary, but I just have a feeling this will be easier. So let's make a little adapter on the back of the tile that converts a signal strength value to one of these values. Okay, I made a little adapter, so now if we put in a signal strength of, let's just say 3, we're going to get the third lamp down, which happens to be an 8. And that's an 8. So now we can do any signal strength 1 through 13 into there, and it'll show us all the numbers we need. In other words, we can now represent this tile with 1 signal strength value. It's right here. Alright, easy part out of the way. Now let's talk about the game logic. Okay, I'm gonna be honest with you, I know how to play the game and I know how the rules work, but I don't really have any good intuition as to how to replicate the algorithm in Redstone. So what I'm gonna do is I'm gonna code it in Python. This is gonna give me a fundamental understanding of the algorithm, and hopefully it'll help spark some ideas about how to do it in Minecraft. You clicked on a Redstone video, surprise, coding. So I got it coded up right here, and we just got 1 class board, and we have a bunch of methods with it. We just use 1 instance of board, and we can play 2048. It's pretty cool. So I'm not going to bore you with the lower levels of the code, but I at least want to show you how it's working, because I think what this is doing is pretty easy to replicate with Redstone. Since all the moves are symmetrical, let's just talk about moving down for simplicity. When you move down, the code makes 3 function calls: compress, merge, compress. Compress just pushes everything down as if there was gravity. It doesn't combine any tiles, it literally just pushes stuff down as far as it can go. Merge then checks to see if there are any tiles that have the same number tile above them, and if so, merge them into the bottom one. Now, why do we call compress again? Well, it's because of a weird scenario that you might not think of, or an edge case. This edge case is where you have 2, 2, 4, 4 in a column. After the first compress, nothing happens because the column is full. Then after merge, the 2's merge into a 4, and the 4's merge into an 8. And you can probably see the problem, we have dead space. So that's why we need to call compress a second time to make sure that all the tiles are fully compressed after the merge. And that's it, that's how you move. Compress, merge, compress. The code just does that for every single direction, down, left, right, or up. It's all the same. So in Minecraft, if we can figure out a way to implement compress and implement merge, we're golden. That's all we need. Let's think about compress first. We need a way to compress these signal strength values towards a direction, kind of like gravity. And I've actually seen some videos of gravity circuits before, so I'm gonna do a quick search to see if I can find any. And oh my god, was that search worth it, because look what I just found. This is a signal strength gravity design by Samos the Sage. I'll link his channel and the video I found this from in the description. You can input whatever values you want here, and they'll line up against the side as if there was gravity. That is amazing. The value you input travels along this main path, which also stores it into memory cells along the way. However, after it passes by a memory cell that it just went into, it deletes it, meaning that once it gets to the very end, it can't go past it anymore, so it doesn't delete it, and it just stays there. In Samos's video, he calls it a first in, first out queue, because that's also a way to use it, but in our case, we're just going to use it for compressing. He's also got his own explanation on there, so if you're confused or want to learn more, I highly recommend checking his video out. Remember, Redstone and engineering in general is not always about doing everything from scratch. A lot of problems have already been solved for you. As long as you understand how it works on a fundamental level, and you're not cheating on a test or anything, there's no reason why you shouldn't use someone else's stuff, with credit of course. Sometimes it's a matter of using your resources rather than using your brain power. Anyways, this thing is absolutely incredible because it basically does compression automatically. We don't even have to think about it. So let's make this circuit do merging as well. Okay, I've been working on it for a little bit. I think I got manual merging working. So if we press this twice, we're gonna get 2 1s, and if we press this button, they should merge into a 2 on the right. Amazing. Just for good measure, if we do 2 of these, which I think are 4s, and then we press this button, they should merge into a 5 on the right. That is incredible. Dude, stuff never works first try like that. The next step is to get it working a little bit more automatically. We need the game to detect if any 2 signal strengths that are right next to each other are the same value, and if so, activate the button. Okay, I think I might have automatic merging working. Well, not completely automatic because you still have to press this button over here, but the idea is once you press this button, that's just going to do all the merging you need to do. All right, let's test it out. So if I put in, let's just do 3, 3, 4, 4. We want the 3s to merge into a 4. We want the 4s to merge into a 5, and then we want it to shift over to the right again. So we want to be left with a 4 here and a 5 here. Let's press the button. Let's go. 4, 5. That's exactly what we want. Now, we could have gotten lucky, so I'm going to put this through a bunch of stress tests, edge cases, stuff like that, and making sure it's 100% working. All right, we have compress, we have merge. They're actually both done in this circuit, which is really cool, but unfortunately, we're only a 1/4 of the way there, because this circuit only compresses and merges in one single direction. If this was our board right here, it would only go to the right. We need to make 3 more of these, 1 for down, 1 for left, and 1 for up, that all do the exact same thing. Doing it to the left is pretty easy. In fact, it's already done. I just flipped the circuit with world edit, but going up and down is a lot harder. We're gonna have to make new designs for those. Oh my god, I take back everything I just said. Look at what Oscar just said. Since 2048 is symmetrical, making it horizontal might be beneficial. That is that is so smart. I mean, look at this. If we make the game flat instead of vertical, he's right. It's way easier. You just take whatever you have and you rotate it around this plane. I'm kind of embarrassed I didn't think of that. I mean, we're done. Now we have all 4 types of movement. The only bad thing about this is we're going to have to redo the display to make it flat instead, but that is a worthy sacrifice. So let's make a tile display that's flat instead. To do that, I'm going to use this mechanic right here, which was invented by Sloime. This is a pass-through circuit that allows you to send multiple patterns to the same display. To create a pattern, you simply replace the yellow blocks with upwards facing observers. For example, let's say I want to be able to display the first lamp and the 5th lamp. I would put an observer here, an observer here. And let's say I also want to display the 2nd lamp and the 4th lamp as a separate pattern. I do that. Now to select which pattern you want, you just press the note block associated with it, which shifts the floor, activates the observers you put in, and sends that pattern to the display. You can clear it with this note block, and let's say I wanted this pattern instead. Now we get 2 and 4. So if we make 13 of these layers, 1 for every number a tile can display, and we stack it so that it covers a larger area, we can use it for a flat version of our 2048 tile. I'll be back when I've made a prototype flat tile. Okay, after I don't even want to say how long, I finally have a working flat tile. It takes a signal strength input right here, just like the other one did, but this time it's on the bottom. That signal strength gets decoded by this blue circuit into a 4-bit binary number right here, and that 4-bit binary number gets sent up into this red decoder. Let me speed up the game real quick so I can show you it. If we put in a 3 and we press this button, we get the 3rd layer, which is 8, or 2 to the 3rd. If we put in a 9 and press the button, we get 2 to the 9th, 512. These are all the 13 layers I loaded, everything from 2 to 8192, and whenever we select a certain layer, that layer just shifts and sends its signal up through the observers, just like in the example. Alright, this is awesome. Our flat tile is completely done. Let's copy this and make it into a 4x4 board so we can see what the game's gonna look like. And there we go. There's our 4x4 board. By the way, I got this Fulbright mod. Absolute game changer. I needed this. Let's recap what we have so far. We have a 4x4 grid of tiles, and we can put any number on any tile we want by putting in a certain signal strength into it, and we have a way to compress and merge those signal strengths in all 4 directions. The next component we need is the one that generates new tiles. First, let's design a way to pick a random spot on the board, and once we do that, then we'll worry about making it a 90% chance of being a 2 and 10% chance of 4. When I coded this in Python, my random generation was done pretty stupidly. It basically picked a random spot on the board, and if it's full, pick another random spot. If that's full, pick again and again and again until you find an empty one. A better way to do it would be to make a list of all the empty spots first, and then you can choose a random spot out of that list. But in Minecraft, I don't really like either of those methods. They both seem hard. I have a different idea that I think is more suited for Redstone. The idea is to look at the rows first and see if there are any that have at least one empty spot, and we'll call those the open rows. Then choose a random open row. On this random open row, we now choose a random empty spot, and that's the random spot that it chooses. So let's say that these 4 input lamps are which rows are open rows. For example, if I flip on this lamp and this lamp, that means that row 2 and row 4 have at least one empty spot. What we want to be able to do is press a button and have an output that selects one random row out of the ones that are turned on. For example, if I press the button right now, the output would have a 50% chance of looking like this and a 50% chance of looking like this. It just chooses one of the random open lamps. Or for example, if this is the only open row, when we press this button, we must get this as an output because that's the only row it could choose. Okay, I've been trying to build something that does this for like 2 hours, and it's honestly really annoying. Maybe I'm just not seeing something, but to me it seems like the reason it's so hard is because you have a variable number of things that you need to choose from. You might need to choose from 2 things, or you might need to choose from 3 things, or even all 4, and on top of that, they're in random spots, and you have to remember which spot they're in to give a correct output. I'll be back when I get something promising. Okay, I found something cool that I think can help us. Someone commented about this on Flappy Bird, and I just forgot about it. It's a shulker box signal strength randomizer. You can load it with whatever signal strengths you want. For example, I'll put in 1, 2, 3, 4. When you press this button, a random shulker box gets dispensed, but they all read a different signal strength, 1, 2, 3, and 4. So basically, when you press this button, you get a random signal strength value right here, 1, 2, 3, or 4. And this is exactly what we need, because imagine the 2nd and 4th row are open, for example. All you need to do is put 2 and 4 into here, and boom, you're gonna get a random output 2 or 4. Okay, thanks to a bunch of shulker box randomizers and a decoder, we now have the circuit we want. You can enter any combination of open rows here, and when you press this button, it will choose a random one from the list of available open rows. So when I press this button, it's either going to be this lamp or this lamp on the output. It's 50-50 chance. If I do all 4, it'll pick a random one out of the 4. Or if I pick just one, it obviously has to pick that one. And what's really cool about this circuit is we can use it for 2 different purposes. We can use it once to choose a random open row, and then once we've chosen a random open row, we can plug its empty spots back into this machine and choose a random empty spot. Because both of those mechanics do the same thing. They take a random 4-bit number and they choose a random spot that has a lamp on. At this point, all of the major components are built. Now it's time for the daunting task of assembly. We need to create a layout that fits all of the components together in a nice way, and we need to think about how we want the game to function within that layout. Okay, I think this is the layout I'm going to go with. In the middle with the pink, we have 16 signal strength memory cells. These cells are going to represent what's on the board at all times, and they should always be one-to-one with what's on the screen, which means that we're going to have to connect each one to its individual tile. Now let's say the player chooses to move up. When they press up, the entire board will be sent into the upwards compress merge circuit thing, which compresses all the tiles up and also merges them with that button down there. After it's done and ready to be returned, it comes back and gets fed back into main memory. Then we choose a random spot with this circuit, generate a new tile, and put it into that spot from below. And with that, we've completed a move. If the player wants to move to the right, it's extremely similar. The board gets sent to these circuits this time, which compresses and merges to the right. When it's done, it brings the board back, and then we generate a new tile. I'm honestly pretty happy with this layout. I think it'll work well. I'll be back when I got some progress on it. Alright, I made some progress, and I moved away from under the board because I was getting a little bit cluttered. I know this is a lot to look at right now, but let me just break it down. The first thing I made is this red circuit. When I press this button, the red circuit takes all the signal strengths that are on here and loads them into the memory cells. For example, if I have a 1 here and a 2 here, when I press this button, the 1 gets loaded into here, and the 2 gets loaded into here. So we're going to use the red circuit to kind of refresh the board when these guys send their stuff back. This blue circuit is pretty simple. It just takes whatever's in the memory cell and it repeats it downwards with a spiral. The reason I made the spiral is so that the orange lines can then grab the information off of that spiral in 4 different planes for 4 different directions. At the highest level plane, you can see we have 4 orange lines, and they're all grabbing information off of the blue spiral, and they're ready to send it in this direction. When you go down 1 level, there's another set of 4 orange orange lines, which are also grabbing the same information off of the blue, but this time they're sending it this way. If you go down another plane, you have another set of orange lines that point that way, and finally on the bottom plane, you have another set of 4 orange lines which point that way. So basically, the orange lines are what allows us to take the board and send it into any other direction. And these purple lines are what allows us to choose which direction we want to send the board. As you can see here, the purple signal is the only thing that's stopping the blue from being repeated onto the orange lines. So based on which purple lines we unpower, we can choose which direction the board gets sent. Now we have a way to send the board to any compressor we want, and then we can also merge it while it's there by pressing that button. The next thing we need is a way to send the board back to main memory after it's done. Alright, I think I made a pretty nice system to do that, and I'll break it down again. Alright, here's the purple memory cells, same thing as before, and the first thing to note is these green spirals. These green spirals are really similar to the blue spirals, except this time they're on top. So for example, if you put a 1 signal strength onto the green spiral, it gets transferred all the way down and it's ready to be put into the memory cell. Back at the compressor, we now have this yellow circuit on top of it. These yellow circuits are basically just the return circuits. When you power this, it takes whatever's in the compressor and sends it into this return line. The return line flows up this blue and goes all the way up here, back into the green spirals. And all 4 sides are the same. They all do the same thing. Okay, now we have a way to send the board in any direction, compress it and merge it, and then send it back. Now let's implement random tile generation. Alright, I made some progress and random generation should be pretty close to done now. You can see we have 2 copies of that random picker circuit that I made earlier. The first one is for choosing an open row. So these blue lines are detecting which rows are open rows and they're being fed into the input. Based on which open row we choose right here, that open row's empty spot contents will then flood onto these pink lines. And these pink lines get sent into the second randomizer, which picks that empty spot on the row. So our open row is right here, our empty spot is over there. All we have to do is use that information to generate a new tile at that spot. Okay, random tile generation is done. This circuit right here is what's going to pick whether it's a 2 or a 4. We just have another shulker box randomizer, which is filled with mostly 2s and then 1 4. So the chance of getting a 4 is actually going to be 1 in 9 because there's 9 spots here instead of 1 in 10 like the actual game, but I'm not worried about it. This is simple, so I'm just going to go with it. The dark green circuit takes that 2 or 4 and it distributes it to every single cell on the board. Then, based on which open row we have, which are these orange lines, and which empty spot we have, which are these orange lines, the only tile that has both an open row and an open spot is the one that's allowed through. And then you just have this blue circuit which allows you to choose when you want it to be allowed through, because you want to be able to control when the tile gets generated. The next thing I'm going to do is I'm going to bring these memory cells out, which is going to be quite a challenge with all this wiring, but remember, these are what the actual game is, so they need to be wired out of here and into the displays above us. Okay, that was way harder than I thought it was going to be, but I finally got the main memory to bus all the way out through this mess and up to the surface. So now this is our board. Now that we have our game, our board, and all of its functions, it's time to make the control logic. Whenever I make control logic, the first thing I do is I just list out all of the functions. We have the purple lines, which sends the board to the corresponding compressors. We have 4 different mergers, and we have 4 different returns. And then as far as generation goes, we have choose open row, choose an open spot on that row, generate the tile type, and allow the new tile into that empty spot. So based on those functions, I think this is probably a good way to wire the control logic. These are the 4 buttons that the player can use: move left, move right, move up, and move down. As an example, when the player presses move left, these 3 things happen: send to the left compressor, merge left, and return. Similarly, if they press move right, these 3 things happen: send to the right compressor, merge right, and return. But when we press any of these buttons, you can see that there's another line down here which always gets turned on no matter what. And that line is connected to the generation of a new tile, because no matter which way they want to move, you always want to generate a new tile afterwards. So let's get to work. Alright, I have a very rough version of movement working. It's just those 3 functions right now: the send, merge, and return. Let's try it out. So I loaded up 1, 1, 2, 2 into the board, and okay, it didn't work, but it kind of worked. I mean, it merged them, but I think the timing on the return journey is a little bit off. All right, I adjusted the timing, so let's try it one more time. We want a 2 here and a 3 here. Come on, give it to me. Yes, dude. Yes. Oh my god, that is awesome. All right, we basically just did our first 2048 movement. I'm not sure it's 100% working yet because it only passed one specific case, but I'm gonna give it a bunch of other edge cases and see if it has any other bugs. Okay, after literally hours of adjusting timings and fixing stupid bugs, I think it's finally 100% working. I put some lamps on it and I put in a couple starter 2s, and let's try it out. So move right, up. Why didn't they merge? Come on. Yeah, I don't think this circuit is gonna work the way I want it to. Dude, I hate redstone sometimes, I swear to God. Okay, let's try that again. Yes, okay, they merged into a 4. Very nice. Okay, it looks like movement is fully working with these buttons, but I didn't hook up the control logic for generating a 2 yet, so let me do that real quick. Okay, everything should be completely hooked up and working. Look at that, we've got moving in all 4 directions, and it's generating a random 2 every time as well. Oh my gosh, that is amazing. We are so close to being done. All we have left to do is hook up these signal strengths to the display. And here she is, the finished 2048 game. Let's try it out. So let's do up. The 4s should merge into an 8, the 2s merge into a 4, and we get a brand new 2 right here. Oh my god, this is actually awesome. Okay, I thought I was done, but there's actually a couple problems. The first problem is that we actually don't want to just always generate a random tile. We actually only want to generate a random tile when the board changes. And that's not me, that's just how the rules work. I kind of just forgot about it. So for example, right now, if I press down, I should not get a new tile because the board doesn't move and there's no merges. But as you can see, I didn't think of that. So I'm gonna put in another circuit that checks to see if the board actually changes. And if the board changes, then we generate a new tile. Okay, should be all set now. Let's try it out. So now when we press down, we want nothing to happen. We don't want a new tile. Okay. Cool. The second problem is with these displays. I mean, they're really cool, don't get me wrong, but they're pretty laggy. They've got a lot of observer clocks and they don't update the lamps properly from far away. For example, if I move up right now, it doesn't actually show it. Like, see how it doesn't update properly? I don't really know what's going on there. I think it could be something to do with the fact that the display is mostly observers. I mean, I could be wrong. I don't know much about the technical lighting updates of the game, but let's just make a display that uses torches anyways. Okay, I've been playing around for a few hours, as you can see, and I finally got a nice torch display. And it's not just better for lag, it's better in every way. It doesn't use pistons, it doesn't use observers, it's completely combinational, and it takes a signal strength input down here, and it doesn't even have a 4-bit decoder on it. It doesn't need one. I mean, it doesn't get any better than this. I don't know why I didn't try to make this at the start. Let's swap out the old displays with the new displays. Alright, I hooked up all the displays and I made a little bit of a cleaner user input. Kind of looks like a controller. The game runs way faster now and you can see all the lamps no matter how far away they are. I mean, this is awesome. And with that, I would say we are done. I'll see you in the showcase. If you enjoyed this video, subscribe, and if you really enjoyed, show it to a friend. I hope you learned something, I hope you enjoyed. Peace out, guys.